Hello everyone, and welcome to today's presentation on fire suppression systems. I'm excited to have you here as we explore the key aspects of design, formulas, and applications based on NFPA standards. Today's session is titled Fire Suppression Systems, Design, Formula, and Application, and will also touch on relevant NFPA codes and how these systems are applied in various building scenarios. In the next few slides, we'll cover the essential elements, starting with the basics of system description, moving into design principles, important formulas, and practical applications in real-world buildings. So, let's get started and dive into the world of fire suppression systems. All right, let's dive into the system overview. Fire suppression works by stopping combustion, and it does this in a few key ways: cooling the fire, smothering it to cut off oxygen, or interrupting the chemical reactions that keep the fire burning. These methods are essential in controlling and extinguishing fires effectively. When it comes to regulations, there are several important codes to keep in mind, including NFPA 12, 13, 15, 17, 17A, 2001, and 750. These standards guide the design, installation, and maintenance of fire suppression systems, ensuring safety and reliability. Now, there's also a simple formula that helps us understand the capacity of a suppression system. Q equals V times C here. Q represents the discharge rate, or the amount of agent released. V is the volume of the protected area, and C is a constant that relates to the system's efficiency. Recognizing these components helps us evaluate and design effective fire suppression solutions that align with safety standards. Let's take a closer look at the CO2 system as outlined in NFPA 12. The design focuses on achieving a total flood concentration, which is typically around 34 to 40% by volume. This means that when the system is activated, CO2 is released into the protected space until it reaches this concentration, effectively displacing the oxygen to suppress fires. To understand how much CO2 we need, we use a simple formula. W equals V times D times C here. W is the weight of CO2 required, V is the volume of the space, D is the density of CO2, and C is the desired concentration percentage. For example, if we have a room with a volume of 100 cubic meters, the amount of CO2 needed would be approximately 72 kilograms. This calculation helps ensure we have the right amount of extinguishing agent on hand. It's also important to note that this type of system is typically used in unoccupied spaces like electrical rooms or generator rooms. Since CO2 displaces oxygen, these areas must be vacated during discharge to ensure safety. Overall, understanding these key points helps us design effective CO2 fire suppression systems that are reliable and safe for the intended applications. Now, let's take a closer look at two common clean agent fire suppression options, FM-200 and NOVEC 1230, which are both classified under NFPA 2001 standards. FM-200 typically uses a concentration of about 7 to 9% by volume, while NOVEC 1230 requires a slightly lower concentration, around 4.5 to 6%. To better understand how these concentrations translate into actual amounts needed, we can use a simple formula. Q equals V times C times rho. Here, Q is the amount of agent in kilograms, V is the volume of the protected space, C is the concentration, and rho is the density of the agent. For example, if we have a room that's 150 cubic meters in size, the calculation shows we'd need approximately 12 kilograms of NOVEC 1230 to effectively protect it. These agents are particularly popular in environments like data centers and control rooms, where sensitive electronic equipment needs to be protected without the use of water or foam. Understanding the right concentration and amount ensures effective fire suppression, while minimizing damage and downtime in these critical spaces. Now, let's take a closer look at the water mist system, which is covered under NFPA 750. The key idea here is that this system uses fine water droplets, each smaller than 100 micrometers, to cool the protected area and displace oxygen. This helps suppress fires effectively without using large amounts of water. The system's formula for flow rate is Q equals A times D, where Q is the flow in liters per minute. For example, if you have an area of 20 square meters and a droplet size of 3, then the required flow rate would be 60 liters per minute. It's important to note that pump pressure for these systems typically ranges from 80 to 200 bar, ensuring the droplets are fine enough and reach the target effectively. These systems are especially useful in protecting high-value or sensitive equipment like turbines, transformers, and even kitchen areas, where traditional sprinkler systems might cause more damage. Overall, the water mist system is a highly efficient and targeted fire suppression method that leverages fine water droplets to quickly control fires while minimizing water damage. Let's take a closer look at foam and wet chemical systems, referencing NFPA standards 11, 16, and 17A. Foam, as many of you know, is essentially a mixture of concentrate, water, and air. When combined, it forms a blanket that covers the fuel surface, effectively suppressing fires by isolating the fuel from oxygen. This makes foam particularly effective on flammable liquid fires. On the other hand, wet chemical systems are specially designed for kitchen grease fires. They typically use potassium acetate, which reacts to cool and smother the fire quickly, preventing reignition. Now, a quick look at the formula for calculating the volume of foam needed. V equals A times R times T here. V is the volume, O is the area to be covered, R is the rate at which the foam should be applied, and T is the time. For example, if we have an area of 25 square meters, a rate of 4 liters per square meter, and a spray time of 5 seconds, that means we need about 500 liters of foam. Understanding these concepts helps us ensure proper system design and effective fire suppression, which ties directly into the overall safety strategies we're discussing today. Let's talk about pump selection, focusing on the NFPA 20 requirements. When choosing a pump, there are a few main types to consider: electric, diesel, and jockey pumps. Each type has its specific applications and benefits, so understanding the differences is key. Now, the capacity of the pump is determined by two main factors: flow and head. Flow refers to how much water the pump can move, while head is the height or pressure the pump can generate. To calculate the power needed for a pump, we use the formula. P in kilowatts equals the flow rate times the head, divided by 367 times the efficiency. This helps us ensure we select a pump with enough power to meet the system's demands efficiently. For example, if we have a flow of 1,000 liters per minute and a head of 90 meters, plugging those into the formula, assuming an efficiency of 0.7, we get approximately 245 kilowatts. This calculation is crucial because it guides us in choosing the right size pump that's capable of handling the required flow and pressure. So, understanding these key points ensures that our pump selection not only complies with the NFPA 20 standards, but also meets the safety and performance needs of the fire protection system. Let's take a closer look at pipe and sprinkler design, starting with pipe sizing according to NFPA 13 standards. The key here is that pipe sizing is primarily based on hydraulic calculations to ensure adequate water flow and pressure throughout the system. The main formula we use is HF equals 10.67 times L times Q raised to the power of 1.85, divided by C raised to 1.85 times D raised to 4.87. This helps us determine the head loss, or friction loss, in the pipe, which is critical for proper system design. When we talk about sprinkler density, it's simply the flow rate, Q, divided by the area, A, in square meters. So, if we have a certain flow rate in liters per minute and know the area it covers, we can determine the density. For example, imagine an office space of 120 square meters. If the sprinkler density is set to 4 liters per minute per square meter, then the total flow rate needed would be 480 liters per minute. Understanding these calculations ensures that the pipe size and sprinkler flow are properly matched to the space, providing reliable fire protection. This connection between hydraulic principles and system design is fundamental to creating effective and compliant sprinkler systems. Now let's talk about cylinder and agent sizing. The key formula we use here is M equals V times C times rho. Essentially, we're calculating the mass of the agent needed, where V is the volume of the space, C is the concentration, and rho is the density of the agent. For example, if you have a volume of 200 cubic meters, a concentration of 6%, and a density of 1.6 kilograms per cubic meter, the calculation would give us approximately 19 kilograms of agent. It's also really important to consider safety margins. You should always add about 10% as a reserve to account for uncertainties, and include a pressure relief valve according to NFPA 2001 standards to ensure safety during operation. Overall, this sizing process is crucial for ensuring effective fire suppression while maintaining safety and compliance. This slide doesn't contain enough information. That's why we're moving to the next slide.